YouTube, right? So we wouldn't want that. All right, now we got the stream. I'm going to get the screen share going here, but before I do that, I wanted to say thank you to everyone for sending me your theme songs. I have not gotten through all of them yet, but I have figured out how to save them to my watch list in YouTube. So I've been clicking and saving all morning so that I have something to go through the next time I'm doing work that allows me to listen to music, which anytime I'm sassing, any coding like that, I can turn the music on. Not when I'm actually writing with words, though. That's a bad combination. But I wanted to send you my choices before I lose my playback here. For my theme song, I have two. So this is my momentum theme song here that I just typed into the chat window. This is Motley Crue's Same Old Situation, another 80s pick, but with an apropos title to describe the pandemic. It is the same old situation for the last year or so, and we are hanging in there. So I have that one. You have to wait till like a minute into the video before the song actually starts. It's like a whole epic thing. And the other one, which is living rent-free in my head these days, as the kids say. Thank you, Kayla, for helping to make me cool. This one is an old Jim Croce song, who was a singer-songwriter in the 70s who was killed like at his prime. And for whatever reason, I'm just really into it lately. So that one is a little more mellow, but it speaks to me. So I thought I'd send those things to you. And now I can start the screen share. Let me get that going. One moment. Maybe I can. There we go. There. I have the formative assessment up for us to talk about. Let me move that out of the way. Okay. Are we ready to do this? All right. And to be honest, I have not made it through all 30 of your responses yet. I think I have about 10 more to go, but I have a good, I think, semi-random sample of how people are responding to these questions. So let me know if you have specific questions about any of this. I will try to hit the high points of things that I read and things that I wanted to elaborate on. So levels, first off here. Several of you were in the clustered multi-level class last fall, and I think are conflating what levels were at that time versus what levels are now. So I want to try to distinguish, because of that, labels that are universal versus labels that are specific to this context. So when I say level 2, words that you can associate with level 2, no matter which class you're in, would be the macro level and between something. So between as the key word there. Analogously, if you're talking about level 1, you can always say that level 1 is the micro level and that is within something. Between and within what depends on the context. And so in this class, in which we're saying people are measured repeatedly as the unit of sampling at level 2, then level 2 goes with between person differences, which are time invariant inter-individual differences. So in this context, because people are level 2, we add those additional words. We can also add the term cross-sectional, because these are pre-existing between person differences that we would have had we only measured them once. Likewise, level 1 is within person, over time, longitudinal, intra-individual, time varying. All of those words go together as well. I had a few folks try and add in fixed and random effects into these things, and that is also true, but not necessarily in the way that you were thinking of it. So in terms of the parts of a model, there's the model for the means and there's the model for the variance. Fixed effects of measured predictors go into the model for the means. Fixed effects can happen at either level. So if I have a predictor that is measured once per person, so a level 2 time invariant predictor, it can have a fixed effect, and it would be a fixed effect at level 2. So a fixed effect would just be like a fixed slope, just like a regular regression model. Variables that are measured at level 1, such as time itself, or any predictor that is measured repeatedly, it can have a fixed effect at level 1. So fixed effects that are slopes that multiply observed predictor variables can happen at either level, any level. On the variance side, model for the variance that describes how observations are related to each other and how they vary. At level 2, the model for the variance contains a random intercept. So that's the next question. At level 1, the model for the variance will contain a level 1 residual. So then there are level-specific terms on the variance side. We use the term random for any variance-related term that is at the upper levels, 2 and higher, and I would use the term residual for any variance term that is at level 1 specifically. Okay, so questions on number 1 or number 2 on any of those words? All right. Then the third one, what is the purpose of a random intercept? So a random intercept, most of you correctly defined, is the difference between the sample mean and each person's mean. So if I have a fixed intercept as the mean of the person means, the random intercept is the deviation from it. So fixed plus random gets to yours. Each person's mean is a function of whatever is in common plus a deviation that is specific to them. And because each person has only one random intercept that characterizes all of their observations, the random intercept is a level 2 term in the model for the variance. And we only care about its variance across people as a model parameter. We don't estimate what it would be for each person. The same as the residuals at level 1. We don't really care what the residual is for each person for each occasion. We care what their variance is across occasions and persons. So what is it for, though, is a different question. If we have a random intercept in the model, what we're doing is taking the total unexplained variability and we're carving it up into 2 piles. So the random intercept is the level 2 between person mean difference pile, and then we have the level 1 E residual within person deviation pile. The reason to do that is to provide a covariance, an association between the residuals from the same person. A random intercept allows those to be related due to the random intercept. So that is the true purpose of a random intercept. It's not the piles per se, it's that making the piles induces an expected covariance between the occasions from the same person, and the expected covariance is constant over time due to mean differences only. That's a key, because there can be other ways that the residuals relate to each other that's not constant, and that's where we're headed in the next unit. Okay, thoughts or questions on any of that? All right, then kinds of ANOVAs. So you all answered this correctly for the most part, some with different amounts of specificity, which is fine. When people use the word ANOVA, odds are good that they are referring to least squares estimation. So because of that, because of the estimation method, ANOVAs cannot have missing data. They cannot have time varying predictors, and they cannot have they cannot have time treated as a continuous variable. It's like time 1, time 2, time 3. Once we switch to likelihood estimation, then we can have missing occasions. But the ANOVA model, in terms of what it says, is what's known as saturated means. So each occasion gets its own mean because you have one intercept and as many mean differences as you need. So if I have 4 occasions, that's 1 mean and 3 mean differences in the model, the slopes. And they differ in terms of their model for the variance. So between groups ANOVA says all of the variance is in one pile, no covariance between occasions from the same person. We know that's not going to be right. Univariate approach to repeated measures ANOVA is a compound symmetry model that has my level 2 random intercept and my level 1 residual, and that predicts the same variance across all the occasions and the same covariance across all the occasions. And then there's the multivariate version of repeated measures ANOVA, or what is known as MANOVA, which is an unstructured matrix in which There is no random intercept and no residual. We don't pile things. We just let the covariance be whatever it needs to be. So we're going to talk more about this today. The idea of a random intercept versus a residual, having a level 2 pile and a level 1 pile. That is a way to predict the total marginal pattern of variance and covariance across occasions, but it's not the only way. So we'll see some alternatives that lie in between those two options in terms of their complexity. All right. I'm talking a lot. Y'all are quiet. Any clarifications or questions? I'm watching the chat window just in case anyone's feeling shy.
So you said that the fixed effects work for both, or they exist, you can have them on both level 1 and level 2.
Mm-hmm.
But with the random intercept specifically, is that, well, am I right in hearing that's only a level 2 thing?
Yes.
Okay.
Yes. So random effects can only be applied to variables that have fixed effects at level 1. So intercept is the first category. Where we're headed is that any predictor that is measured within persons over time can also have a random effect across persons in addition to the intercept. But yes, you can tie
Gotcha.
random to level 2 in your head. You can just make that association.
Okay. Thanks.
Thanks for the question. Other questions? Internet issues out there? Yes, no worries. If the internet drops you, you can feel free to come back in. The doorbell will ring. I'll let you in. I've gotten pretty good at like monitoring all the screens here. Not to like toot my own horn, but I hope I'll let you in within at least a few minutes of you dinging the doorbell. So you would think after however many months of practice that I could at least do that much. So no worries about any of that. All right. Okay. Then if there's no other questions, oh, I remember what I was going to show you. After class last time, I had folks asking questions about what was in the model, and so I revised the handout for example 3B to have some more stuff in it in terms of labels, and I just wanted to point that out to you. So I'm pulling up 3B briefly. These were the 3 Anovas, so they each have the same saturated means model. So in this handout, let me find, here it is. So that equation right here, this is on page 2 of example 3B. That equation describes how the model for the means has included a fixed intercept and number of occasions -1 slopes that fully differentiate the mean at each possible occasion. So this is known as saturated means. You can think of it as just treating time as a categorical predictor. So we're not putting a slope through it. We're letting each occasion be whatever it wants. And I have it set up so that the last occasion, which is session 6, is the intercept because that is how it is parameterized in SAS, and I have made R and Stata do it the same way. And so because of that, each of these variables in here, T1, T2, T3, these would be binary variables that just turn on for a 1 if it's that occasion and 0 otherwise. So beta 1 is the difference of how time 1 compares to time 6. Beta 2 is the difference of how 2 compares to 6 because 6 is the reference. So all in all, I have 6 betas. They're going to perfectly recapture the 6 means. This, by the way, will only match the means in your observed data if you have complete data. If not, they will give you different answers. Same old dummy coding? Correct. Same old dummy coding. That's what this is doing behind the scenes. So I am letting SAS do that work for me by taking this session time variable and putting it on the class statement. So for those of you from 6242, this is the last lecture we didn't get to that I recorded videos about. This is being treated as an I.dot variable in Stata to do the same thing. And in R, it's being treated as a factor variable. So I'm letting the program do the dummy coding for me contrasting each other occasion relative to a reference occasion. And so what I did after class last time in comments is add the betas to the output. So the solution for the fixed effects here, I have labeled each of the values, how they correspond to what the betas were in the equation. And then the table down here labeled least squares means, I have indicated how those came about. So the mean for session 6 is directly given by beta 0. To get to what the mean was at session 1, for instance, it's the reference mean for 6 plus how it differs for 1, which is beta 1. Likewise, the reference mean plus each of the subsequent differences for the other means as well. So I just added these in here to be a little more transparent as to what's happening. So that's one of the conveniences as to treating time as a categorical variable, is that one line of code gets you all of this. It gets you the model parameters, it rearranges them into expected means, and then you can also ask for the next table here. All possible mean differences between occasions is one line of code for all three of those things. So it is same old dummy coding, just under the hood, it's doing all this stuff for you. I don't start teaching it that way because it's less transparent as to what is going on, and I want you to have the linear model representation to pull from when you're looking at this stuff. So I thought that might be helpful. So any thoughts or questions before I shut this one down, switch back to new stuff? All right. In general, I will try to do that across my handouts to label things that way, except when it gets to be too much. All right, where is lecture 4? Here it is. Okay. Alternative covariance structures. That's what we're here to talk about today. Let me make sure yep, the recording's still going. I'm good shape. So this is then changing topics a little bit, moving out of what could be done with least squares. So if you've had any repeated measures, Anova, multivariate kind of content from that old school perspective, that ends now. So the options that I'm talking about from this point forward are really only available if you have likelihood estimation. These are additional options that are available to you. And we have new terminology and new letters to go along with this. So alternative covariance structures. So big picture, what are we talking about? Within this unit, so lecture 4 and example 4, we are focusing on the case where your longitudinal data would take this form here on the right. So fluctuation rather than change. So studies in which sampling over time is just a way to get within person information and you don't really care which time is which. So daily diary kinds of studies where your phone beeps you and they ask you about your mood or if anything stressful happened or what your diet looked like or how much exercise you've gotten, these sorts of things where you're just sampling experiences. I think experience sampling is a word. That's what we're talking about here. So we do still have to worry about modeling time correctly, but the tendencies that time is going to have in these sorts of designs is very different than the tendencies that time will have over here on the change side. So we're starting with the right-hand side here. In next week or the week after that, we'll move into change. So because time isn't really part of the story, the model for the means in each of these cases may not even have time in it. Time might not need to be a predictor. Like if I look at this picture here, to the best of my PowerPoint drawing ability, there are no mean differences across time. People vary across time and they may vary differentially, but it's not like time 2 is higher than time 1 and time 3 is higher than time 2 or anything like that. So time may not need to be a predictor in the model for the means. It may not need to have fixed effects. However, we do have to worry about it in the model for the variance because we need to worry about whether or not the occasions have different variance and whether the pairs of occasions have different covariances depending on which occasions they are. Those are the things that we have to worry about. So here's the spectrum of possibility. On the left-hand side here is compound symmetry. This is our friend random intercept plus residual two-pile model, univariate repeated measures Anova. And this idea that the variance at each occasion, so in these matrices, this would be like a 4 occasion example, where the diagonal, row 1, column 1, row 2, column 2, 3, 3, 4, 4, those are variances. So the variance of occasion 1, 2, 3, 4. The off diagonals, those are covariances. So you can think of those as the deviation on one variable from the mean times the deviation from the other variable from the mean. They are unstandardized correlations. So the association tells you the direction of the relationship. So positive numbers mean positive correlations, but they're in the scale of the original variables. So these are covariances. These are variances right here. And this structure right here, compound symmetry, is a very strict assumption that the variance stays the same across time and that the covariances stay the same across time. So occasion 1 and 2 are just as related as occasion 1 and 4. So a fairly strict assumption, but at least the model does say that there is an association between occasions from the same person. So it is plausible for longitudinal data, but it's the simplest model that we would probably ever see for longitudinal data. So on the side of sort of parsimony, this is a 2-parameter model for the variance. A U variance and an E variance, and they do all the work. Okay, with me so far? Now, on the other end of the spectrum here, on the good fit side, is unstructured, let everything be what it wants. So this is the multivariate approach to repeated measures ANOVA. This is your H1 in the SEM language. The idea that we're not trying to pile things or predict things or carve things up. We're just letting it be whatever it wants. So this is whatever the data say the variance is at time 1. This is whatever the data say the variance should be at time 2. This is the covariance between 2 and 1. This is the covariance between 3 and 1. And this will look just like what you would get out of ProcCore or any procedure that generates a covariance matrix for you if your data are complete. If your data are incomplete, they will not match. This is what your data would have given you had they been complete, is what maximum likelihood is trying to recreate. So this is the right answer, so to speak, of what your data want to be. This unstructured matrix is only possible when you have balanced occasions. So balanced is when everybody shares the same measurement schedule. There's a time 1, there's a time 2, there's a time 3. It doesn't have to be equal interval. So you could have a study where people are measured at pre-test and post-test is 2 months later, and then there's a 6-month follow-up after that. Like that's still balanced if everybody came in at exactly those 3 times. But if some people came back 2 months later and some people came back 2.5 months later and some people came back 3 months later, so there's noise around when time 2 was, that's unbalanced. And that kind of inconsistency in when time is means that this matrix can't work. You can't have intermediate rows and columns here. So unstructured presupposes that there is one matrix that can summarize everybody's observations and you can just let it be what it wants. So this don't work when we have balanced data, and this don't work when we have so many observations that it's not possible. Because if you look at the number of parameters, there are 4 unique variances and 6 unique covariances. So for 4 occasions, there's 10 things to estimate right off the bat instead of 2. If I had 5 occasions, there's 15 things to estimate right off the bat. So this gets to be unwieldy for longer studies. Okay, with me so far? Still, I should say. So somewhere between the two is where we live now. And I have named that structure, which is a reference to what used to be an 80s game show called Name That Tune. It is back. I think it's on Fox, but it is back. And Elaine, what's her name? Oh, I'm blanking. Very funny actress.
Julia Louis-Dreyfus.
Not that one. She was on 30 Rock and she was on Ally McBeal. Oh, darn it, I can see it. Jane Krakowski. That's what I'm going with. She is the host now. She's very funny. Anyway, Name That Tune is back. And it's like Beat Shazam that I was in love with a couple years ago, but it's less fun because I can't play on my phone and beat the contestants, but it is back. But the premise of Name That Tune is just like it sounds like the band plays a song and you buzz in as soon as you know what the name of the song is. But for drama, the contestants have to battle. And so they give some sort of clue, and then someone says to their opponent, Sue, I can name that tune in 10 notes. It's like, Bob, I can name that tune in 9 notes. And they go back and forth until somebody says they can name the tune in 1 note. Like, for instance, one of the clues, this isn't as hard as you would think. This Titanic of a hit will never end. It's like, okay, I can name that tune in 1 note. My Heart Will Go On by Celine Dion. The end, right? Those are the kinds of clues that allow you to name the tune in 1 note. But I borrow this as an example though, because we're playing Name That Structure. And the number of notes is the number of parameters. And it's like, okay, how many notes do I need to get that matrix right? Does it only take 2 notes? Like it's a super easy matrix to approximate. I can do it with compound symmetry and that's close enough. Does it take all the notes? So unstructured is like playing the whole song, right? It's not Name That Tune if it takes you the entire song to get to the title of it. So somewhere in the middle, we're trying to get a fit that is not worse than what unstructured would be with fewer than all possible parameters. So we would go through this process whenever we have the answer key to see if we can get away with something simpler. But it's even more important when we don't have the other end. So when we have unbalanced data or so many occasions that unstructured isn't possible, then we have relative fit comparisons in the middle here to sort of guide us as to how many notes are sufficient to be able to name that structure. So we live in the middle here. And in terms of the choices for what the structures could be, this week we're talking about what I call alternative covariance structures, which are designed for longitudinal data that show fluctuation. Stay tuned. Next week's episodes, or maybe the week after that, we'll see, we're going to have random effects of time that do the same thing. Random intercepts and slopes for change are another way of making a structure that captures the information in the unstructured matrix. They are another way of doing the same thing. So that's what we're going to do. So I got to be honest with you, this material is probably like the most boring chapter in the whole book. It was boring to me to write it, and it's going to be boring to you to read it. It's not interesting. But it is important from the perspective of getting the things right that we do care about. So I have lots of like real life examples that I try to like sprinkle in here to keep us awake, but also to give you some sense of like, what are we even doing this for? And another real life example I can draw from this is the process of painting a room in your house. How many of you have had this experience of learning how to paint? Anyone? A few people? So I remember, I think some people were talking about it last semester, buying new houses and painting. Yes. Turns out that what you see like on the home remodeling shows where you go to the paint store and you pick out the perfect color and then you go home and slap it on the walls and the whole thing looks great in like 3 hours, that's not what happens. The real process of painting a room starts with you painstakingly removing everything from it, the walls, sanding, filling holes, taking down all the light fixtures, taking down all the electrical outlet fixtures, carefully taping all of the edges of the ceiling and the carpet and around the closet doors and everything. And after you spend 3 days very carefully preparing your room, then maybe you can put the paint on. And then you realize that it turned out too yellow, and then you go back to the paint store and you pick out another one, and now it looks too orange. And then you keep doing this until you finally get to the right shade of yellow, or you just give up and decide that it's good enough, right? Nobody likes that process of doing that careful preparation work, but it's necessary for your paint job to not look like crap. Nobody likes testing alternative covariance structures. Oh, does unstructured fit better than compound symmetry? Like, no one woke up with that question burning in their mind. No one cares. But in order to make the paint job look good, in order to get the right standard errors for your fixed effects and have the p-values be believable, we got to go through the process. So this is like the underlying effort that it takes to properly support your model. And I believe that it should happen straight off. It should happen first before you add predictors, because having those predictors effects be believable is predicated on having the right model for the variance. So if you start with the wrong model, the whole model building process can go awry. So that's why I say we do this first, we get time nailed down, then you can add your predictors and see after you're done with your predictors whether you need to tweak anything, whether you can get by with an even simpler model or not from that point forward. So this is the prep work. That's what we're doing. All right. Deal? Prep work? And a few of you have stopped by office hours and asked me questions that are along these lines, like, what are we doing this for? Or what's the point? Those are totally valid questions, and I actually encourage you to ask them, because this stuff can be technical and it can be very like overwhelming in its level of specificity, and helping to maintain the big picture of what this is for, I think will help in helping you to sort of know where to put the details in building a memory structure for this information. So please do ask those sorts of questions, and don't think you're the only one who has them, because I can guarantee that you aren't. All right. So reviewing, how do we know if something is good enough? How do we know if unstructured fits better than a simpler alternative, or our simpler alternative fits worse than unstructured? A brief review of those ideas. Relative fit is how. So in terms of doing hypothesis tests, comparing nested models to see what we need and what we don't need, the way that we do that in this class is going to depend on how the models are nested, whether they differ in terms for their fixed effects or whether they differ in terms on their variance side. If it's the fixed effects, so if you're at the point where you've done all this prep work, you've got your model, and now you're adding the predictors that you care about, you don't have to worry about any fit assessment whatsoever, because you can rely on the univariate and multivariate wall tests that come with your predictors. So the reason that you never had to hear about this, say in a regular regression class or a linear models class, is because you don't need relative fit. It wasn't a thing that was necessary. You stare at the p-value that shows up next to your t, or you stare at the p-value that shows up next to your f, and you make conclusions. We can't do that when we're deciding which structure fits relatively best. Instead, we have to use relative model fit comparisons based on -2 log likelihood. So we cannot use the p-values that show up on the output. So SAS and a few other programs will give you z's that go with your variances, where you have an estimate for your variance. It comes up with the standard error for that variance, and it will give you a z-value as to whether or not that estimate is different than 0. We can't use them, because those are predicated on the idea of a normal distribution for what the variance could be. Its sampling distribution around the null hypothesis is supposed to be normal, but if the null hypothesis is 0, then we're missing the whole negative side. So those tests will get more wrong to the extent that we're closer to 0 when we need them to be more right. So even though p-values show up on the output next to your variances, we're not going to use them. In almost every case, we're going to do -2 log likelihood comparisons instead, what we started talking about at the end of last time. Actually, we didn't get through last time. That's right. At the end of 3B, we didn't get there. Let me spoil it for you. Unstructured fit best. That's what we missed. So I did a likelihood ratio test to compare compound symmetry, univariate repeated measures Anova to the unstructured multivariate, and the one with more stuff in it fit better. That was the end of that. We'll get a chance to practice it in this one too, so I'm not going to sweat it. All right. So relative model fit. We talked about this last time, but it's sufficiently hard to wrap one's head around that I think it's good to go back over it. your output is going to come to you in one of two forms. It's either going to come as likelihood, log likelihood, or -2 log likelihood. Usually not likelihood, so we can ignore that one for all intents and purposes. If it's log likelihood, that's LL, that is height. So it is the height of your data given the model parameters, and in this class, using the multivariate normal distribution as the formula for how we get height. So bigger is better if it's log likelihood. It is more likely it is taller if it is a bigger number. The same goes if it's a negative number, by the way. If I have like -20 versus -10, -10 is bigger. So it works the same direction regardless of whether you're on the negative side or the positive side. So log likelihood bigger is better. Cough, cough, homework question. If you have -2 times the log likelihood, which is what SAS gives you and SPSS gives you that, they're trying to help because you're eventually going to have to multiply the difference in log likelihoods between values by -2 to make it a chi-square. So they're trying to help you out by sort of saving you that step. But in doing so, they change the direction of what is up. So if your output, like SAS or SPSS, gives you -2 log likelihood, then smaller is better because it is not height, it is shortness. So smaller is better when it comes to -2 log likelihood. Bigger is better when it comes to log likelihood. So the process then for comparing two models in terms of their fit is the difference in -2 log likelihood. So if you're given -2 log likelihood like in SAS, it's just the straight difference between models. You can eyeball it. If it's given as likelihood, then you have to take the difference in the same direction and then multiply it by -2. So either way, you come out with the same number. That number should be positive. The smallest it can be is 0. If you got a negative number, something went wrong. So order of operations matters here. In your first homework, there are several multiple choice questions asking which of these would result in a valid likelihood ratio statistic. That's this. So what I'm looking for in those questions is to see that you're able to get the order right as to which of the two models that I'm referring to in the question has fewer parameters versus which one has more. And then also whether the models differ in their model for the means or their model for the variance or both. Because you can compare any two models in ML, you can only compare models that have the same model for the means in REML. So that sort of rule set is what those questions are asking. So fewer minus more matters in direction. In terms of the difference in number of parameters, though, it's backwards to keep that number positive as well. So the degrees of freedom for the test is the number of things you've added, or you can think of it as the number of things you've taken away. Subtracted, excuse me. I'm used to talking about math with a 5-year-old. So he knows what addition is, and if you're not doing addition, you're taking away. So 7 take away 2, for instance. So we're adding parameters or we're taking them away. And then the difference in -2 log likelihood is distributed as a chi-square. Put a star next to that because it's a slightly more complicated, but we'll get to that later. Ish, chi-square-ish, close enough, with differences in the number of parameters as the degrees of freedom. So that means that if you add one thing, your -2 log likelihood needs to go down. -2 log likelihood of shortness goes down by 3.84, which is the chi-square degree critical value at alpha of 0.05. If it's two things, it's 5.99. If it's three things, it's 7.82. And if it's four things, it's 9.49. You don't have to memorize this shit, though. This is like old school Lisa who had to look this up in the back of her textbooks. There was like a table there. These are functions. So in Excel, I give you spreadsheets that go with all of my examples that were from the book in which I've worked out these likelihood ratio tests. There's a function called chi-dist where you plug in the difference in -2 log likelihood as one argument to the function. You plug in the degrees of freedom, and then it spits out the exact p-value. LR test is a command that's built into Stata to do this, and Anova is even though it's Anova, when I first heard that, I was like, oh, that can't be right. Anova does likelihood ratio tests? What? But no, that's what they called it. So yes, Anova option in R does likelihood ratio tests, and there isn't one that's built into SAS, and so I built you one. So I have a macro program in SAS that is called fit test that does this for you. And so in all of my examples, I am using that to get the same information that I would get out of other programs. So this is how we're going to decide whether or not we need something that's unstructured or whether we can get by with fewer parameters, whether we can name that tune in fewer notes. Okay. Questions? So this is the exact same process that is used in generalized linear models. This is used in structural equation models. This is used in IRT models. If you've heard of this before, it is the same thing. It's just a difference in terminology. So the formal name for this process is a likelihood ratio test. That's because it's actually a ratio of likelihoods from the models. Once you take the log, then it's a subtraction rather than a division, the same way that once you take the log, things that were multiplied get added. So that's where that term comes from. You can also think of it as a deviance test in the multi-level modeling literature. That phrase is sometimes used, and it's known as the chi-square test in SEM because your chi-square of absolute model fit is a likelihood ratio test against the unstructured model of whatever your factor model is going to be. By the way, brief aside, moving back 2 slides because I just thought of it, this whole thing of name the structure, trying to find something that's in the middle that does as good a job as unstructured, that's what factor analysis is for. A confirmatory factor model is a structure that is trying to capture the unstructured model using fewer parameters. And actually in SAS mixed, there is an FA structure that will do this for you. So putting the two worlds together. If you haven't had SEM stuff, you can ignore me whenever I say things like that. That's totally fine. All right, we were here. So then, as we said last time, in terms of how you talk about the results of these likelihood ratio tests, if the difference between models is significant, the model that has more parameters fits significantly better. The model that has fewer parameters fits significantly worse. You can phrase it either way. Whichever one makes more sense depends on the context of what you're doing. If you're talking about starting from a simple model and adding things, like if I have a one pile of variance E-only model and I add a random intercept, my goal in adding something is to make the model fit better. So a likelihood ratio test would be phrased as adding the random intercept either made it significantly better or not significantly better. In this context, if I'm starting from unstructured as the right answer and I'm trying to find something simpler that does as good a job, then I would phrase it the other way. I would say that my simpler model fits either significantly worse or not worse. If it's significantly worse, it means I shouldn't keep it. If it's not worse, then that means they're equivalent and that I was able to name the whole song in fewer than all possible notes. And this bottom part here is what you need to do homework 1. The very first part of it is a vocabulary exercise where I'm asking you, given a value of -2 log likelihood, to compute what the AIC and the BIC would be under ML versus under REML, because which parameters count in terms of this multiplier right here depends on whether you are in ML or REML. If you're in ML, it's all the parameters, so all the fixed effects in the model for the means, all the random effects, residual variances, and any sort of covariance thing in the model for the variance, whereas in REML, it's only the model for the variance parameters. So all those calculations are just designed to get you familiar with these rules. That's what they're for. And each of you has a different -2 log likelihood value to start with and should apply the same calculations to be able to get AIC and BIC. And so this is why in the instructions for the homework, I suggested that you build yourself a spreadsheet with these rules in it. That way you can go through the questions super fast. The only question you have to answer is what counts in terms of model parameters here, whether it's all of them or just the variance side. So this is the slide that I had referred to in the instructions that has the way to find these values. So, all right, I think that's, yep, changing gears. So any questions on how to do model fit stuff? We're going to get lots of practice with this, but this is just the overall procedure. We're good? Goodish? Good enough to go forward at least? Okay, so in this set of options, we're going to be paying attention to, thank you for the yellow thumbs, we're going to be paying attention to basically two features of the data. In terms of the variances across occasions. Did I just say across? I think I put a T in there. Okay, I need more caffeine. That shouldn't happen. I may say root instead of root, but across is not a word. Okay. Variances across occasions. These models that I'm going to talk about here have two choices, same or not the same. That's it. There's very little flexibility. The models that are coming later have more flexibility, but these ones are very rigid, same or not the same. If they are the same, it is a homogeneous variant of the model, and if they are not the same, it is a heterogeneous variant. So two flavors. In terms of the covariances across all the possible pairs of occasions, they can either be the same, all different, or sort of same, sort of not the same given a particular pattern. So there's more flexibility with these here. And so each of the structures that I'm going to give you varies in these two dimensions as to what they say the variances should be, either all the same or all different, and what they say the covariance pattern should look like, whether it's all the same, all different, or something in the middle. Most of these options, though, that we're going to talk about today, though, are fairly limited because they're based on the idea of a time lag. So the idea of a time lag is the distance between occasions, and a lot of these structures presuppose that the distance between occasions is the same across all your occasions. In other words, that they're equal interval. So the distance between time 1 and 2 is the same as the distance between time 2 and 3 is the same as the distance between time 3 and 4. If that's not true, then some of these aren't going to make any sense. And I'll tell you which ones. They all require balanced data, except for one. Any of the ones that have different variances across time require balanced data for sure, anything that's heterogeneous. But none of them require complete data. So we're in the world of likelihood, we're not in the world of least squares. That means we use whichever occasions a person has data for, and we don't use the occasions from that person that they don't. So a person can contribute to the extent possible. And the job of the likelihood estimation process is to try and recreate what the patterns of the variances and covariances would have been had the data been complete. That's what it's for. More details on that coming later. But we do have to have some new terminology to describe the possible choices for this. We got some letters and some words that go with this. All right. Letters. So you've seen one of the letters already, R. And in what you've seen so far, R has been used to label the variances and covariances over time. So all of them in one matrix, where the diagonal is variances and the off diagonal is covariances. That's R. We're going to look at a set of models that use only R to address the correlation of occasions from the same person. So everything happens in one place in one matrix. And I call those R-only models. because R is the only thing that we're working with, paying attention to. The other options add another letter, which is G. And these options distinguish a random intercept from other things. So there are certain combinations where you can get to the same model two different ways that I want to explain to you because it's useful for you to understand how these two things fit together. But these are sort of two different strategies for going about this process. And I would say that in general, I have found the latter, these GNR combined models, to be more useful for longitudinal data. The former, the R-only models, I'm mainly teaching you so that you know what they are if someone talks about them. They are generally not as useful. In practice, that's what I have seen, but I want you to know what they are. Because when reviewer 3 starts shooting their mouth off about what kind of model you picked, I want you to have a good response. That's what I'm going for here. So R and then adding in G later on, but we'll get to just R to start with. Okay, are you ready? Look at some of these. Okay, so the thing about these R-only models, most of them are not trying to make piles. Everything is happening in one matrix. So they're trying to do the same thing. They're trying to allow the residuals from the same person to have a relationship, but they're doing it all in one space, so to speak. So we're going to be phrasing them in terms of what happens to the total variance at each occasion and the total covariance. And by total, I mean marginal, like all in one place all together. And I have included labels for what SAS calls these things because SAS doesn't always use labels that are terribly helpful, as you might imagine. We are going to look at, in the output, what the model says happens in terms of the original variances and covariances, that's R, as well as what the model says that translates to in terms of correlations. That's our core. So those two pieces of output will help us understand what's happening in terms of the structure. And I remind you that unstructured always fits best by -2 log likelihood. So in terms of absolute fit, it is the right answer. In terms of AIC and BIC, though, it's probably not going to like it the best because AIC and BIC take into account how many parameters were used. So we're looking for things that fit not worse than unstructured. That's the end goal of this process. And I have a note here that unstructured models take forever to fit in Stata. So if you're running these things yourself, be prepared to wait. I don't know why that is, but that's what I have found across all different data sets. And also, the code that I'm going to give you in R to do this does not have correct denominator degrees of freedom. So I have a note about that, more detail coming later, but this is one problem that I have not been able to solve, and I have asked several people who know R better than me, and they couldn't solve it either. So I don't know that there is a solution. So I want to point that out, that some of these things are going to have slightly different fixed effect denominator degrees of freedom across programs because of differences in how the program handles these things. So here are two, and one of these you know already. First up is our friend compound symmetry. So this is an R-only model because the way that it is phrased is by taking the total variance and carving it up into two piles here. The CS parameter is your random intercept, and it shows up on the diagonal as part of the total variance, and it shows up on the off diagonals as the covariance. So this is what you've seen so far. So this is the idea that the only reason why occasions from the same person are correlated is because some people are higher than others on average. That's the CS parameter here. This is a very restrictive structure because no matter how many occasions you're trying to fit this to, it only uses two notes, two parameters, the random intercept CS parameter and the residual variance parameter here. Those two parameters do all the work. So I have another system of analogies that I use to describe the fit of these matrices. Would you like another real world example to hang on to when we talk about this? Pants. The example is pants. So think about the way that different kinds of pants fit. Now, for those of you who remember what happened before the pandemic, pants were things that had zippers and buttons, and like they were uncomfortable in a lot of times. So in my world of like possibilities here, the unstructured matrix is like sweatpants or athleisure wear. It's going to fit no matter what, right? If you outgrow your sweatpants, something has gone wrong, right? Sweatpants are generous. They always fit no matter what. Compound symmetry is like skinny jeans. They're very restrictive. They're not for everybody. Compound symmetry might fit some longitudinal data sets, but there was never a point in my life where skinny jeans would have looked good on me. And there will never be a point in my future that skinny jeans are going to look good on me. I don't want skinny jeans. I want nothing to do with them. Some of you may love them and wear them and rock them, and Godspeed. I am not one of those people. But they're restrictive, right? It's a very like, picture the tiny legs restricting you, variance all the same all the way down, covariance all the same all the way down. Compound symmetry has a cousin that allows different variances across time, and that's compound symmetry heterogeneous flavor. This would be like skinny jeans that come from Kohl's or something, like they're not from the juniors department. They have a little more breathing room, but not much. They're not jeggings for God's sake, right? They're pants. So the CSH thing here frees up the diagonal so that the variances can change over time. And so note that there's only two flavors at work here. Either the variances are all the same or they're all different. In CSH, the way that the covariance gets created, though, is still with the same correlation ingredient at each occasion. So this model has a correlation that is labeled as CSH on the output. And then that correlation is held constant across all of the pairs of occasions. So CSH is like a compromise. It's like, okay, let the variances be different across occasions, but the correlation between occasions is the same. And this is how we convert a correlation into a covariance. It's the correlation times the standard deviation of each of the variables that go into it. So the covariance changes over time because the variances do, but at the root of that relationship is the same correlation across time. So it's still a restrictive structure. So those are two options that we may have available. This one, by the way, CSH, is only available in SAS. It's not available in Stata. I think I could trick R into it, though. I think I know how to do that. So this one is not as readily available. So those are two. If you want to say that no, the correlation should not be the same across time, it should depend on how close the occasions are. That seems like a more reasonable prediction. Then I've got some more flavors for you. Autoregressive. So AR1 stands for first order autoregressive because there are other orders possible in the world, although they're not in SAS. And this one is built on the idea of a correlation that decays exponentially with time. So the way that this works is that all of the correlations across occasions are functions of one parameter r. So if you look at the first off diagonal here, so the correlation between occasions 1 and 2, 2 and 3, and 3 and 4, that right here, R1 is in all of them. So what this model says is that the correlation between all adjacent occasions is captured by an R. The correlation between occasions that are 2 apart is captured by r squared. 3 apart is captured by r cubed. 4 apart is r to the fourth. Fourthed, quadth. Is there a word for that? Anybody? My vocabulary stops at cubed, but it seems unfair that r to the fourth doesn't have a word for that. But point is that there's only one r being estimated, and all the others are related to it. So the occasions that are 2 apart, so 1 and 3, 2 and 4, those are that same r parameter squared. Quadrupled? Okay, we'll take that. R quadrupled. Although that sounds like it's r times 4 maybe, as opposed to r to the fourth. Yeah, r to the fourth, that's what we're doing here. So, and we don't have an r to the fourth because I only have 4 occasions. R to the fourth would be if I had 5. So there's only one parameter in this thing for the r's, and there's only one parameter for the variance. So this is a structure that says the variances stay the same over time. The correlations decay over time. They decay in this r to the first, r to the second, r to the third, r to the fourth pattern. For those of you who've seen longitudinal models in path analysis, like a row of boxes where like one box predicts each other, like time 1 predicts time 2, predicts time 3, predicts time 4, that's this model, except as fixed effects. Because the model predicts, it would be like to get from 1 to 3, it'd be the 2 paths multiplied together. To get from 1 to 4, it would be 3 paths multiplied together. So it's the same sort of idea. Okay, let me look at the time. Okay, are you with me? Autoregressive, 1r, square it, cube it, fourth it, fifth it to get to all the relationships. Now, what could possibly go wrong? And before you all got here, I had to pull up what could possibly go wrong. Autoregressive correlation is like tapered genes from the 80s. Now, I know many of you were not alive and did not participate. So I brought up Google Images to educate you with. So this look right here, for instance. Big, like high-waisted, so high-waisted that they had to roll it over, mind you. This is a special kind of 80s pant. And then down to the taper. And for those of us who didn't have parents who bought them designer jeans, thanks, Mom. I'm still not cool. I'm still not over it. We decided to make our own taper with this right here. So this bad boy, and also this one. This is what's known as peg rolling. And this is what we used to do on purpose to our pants to make them taper as much as humanly possible. So I know some of you are nodding. They're like, yeah, I did that. I remember doing this. So this is a look, and I'm sure there are people who can rock this look. But this is what is now known as like mom jeans, right? Where you have the big waist and it's high-waisted and it's narrow. And what's wrong with this look on, say, your average middle-aged person who might still be rocking it is that it makes your butt look huge. Like the tapering is not your friend. So I used to watch this show, What Not to Wear, with Stacey London and Clinton Kelly on TLC. It's a wonderful show. They used to surprise people on the street and give them makeovers. So their friends and family would send in video of people looking around, like walking around terrible, and they'd get a makeover out of the deal. Yes, great show. And invariably, when it was like the dumpy middle-aged person, this was the crime that they were being arrested for, was tapered jeans that just they make your ass and your thighs look huge and they do you no favors. And once they put them in a straight leg jean, wonderful things happen and they look lovely. So the same problem that is happening with these pants, that they narrow too much, is happening with the autoregressive structure. It narrows too much. So if I have, say, a correlation between occasions that's 0.6, if my R is 0.6, then occasions 1 apart, lag 1, are correlated 0.6. Occasions 2 apart are correlated 0.6 squared, which is only 0.36. And occasions 3 apart are cubed, which is something I can't do in my head, but it's a lot smaller. Yes, thank you. You know what, Nikki, I come to teach, right? It is my job to make sure that you are educated in all the important things like autoregressive matrices and fashion. It's very important. But yeah, it's the same problem though. The pants narrow too much and the matrix narrows too much too. So it predicts pretty quickly that there is no more correlation between occasions from the same person, and that's just not true. Even occasions far, far apart in time, if they come from the same person, tend to have some correlation there. So autoregressive narrows too much to be useful. And then it has a cousin, ARH, which is the heterogeneous version, which has the same problem of narrowing, but at least it lets the variances be whatever they want across time. So those are some options for you. So we've got so far skinny jeans, which is compound symmetry, tapered jeans, which is autoregressive here, and then next slide, topolets, which I'm going to call bootcut, because bootcut could mean a lot of different things. In some stores, bootcut is what they call just a straight leg pant. And in other stores, bootcut has like a flare, like there's room for your boots at the bottom, which is what you would think it would be called. And just like bootcut can mean a lot of things, this structure, topolets, can take a lot of forms. So this one here, let me get this back 1 second. There we go. Move the thingy out of the way. This structure is similar to autoregressive in that it predicts different correlations depending on how far apart in time the observations are. So like I have this CT1, CT2, CT3. So all of the correlations that are 1 unit in time apart are C1. All of the correlations that are 2 units apart are C2, and so on. And these are phrased as covariances when it's homogeneous variance and as correlations when it's heterogeneous. But the C's are separate. They're not squared or cubed or fourthed or anything. They're just separate. So you could have like a correlation between adjacent occasions that's 0.8, a correlation between occasions 2 apart that's 0.75, a correlation between occasions 3 apart that's 0.7, something like that. So it allows different correlations between occasions based on how far apart in time they are, which makes sense, but it doesn't force them to decay exponentially. So it takes more parameters. There are as many parameters in this as you have occasions, and this only makes sense if your occasions are equal intervals. So I call this one bootcut because it could look like a straight leg pant. These all the C's could be equal. The C's could grow over time. It could actually look like a flared gene, or it could look like something that's still narrowing a bit. The C's could be smaller as you go on in time. So it's kind of a chameleon. And then the heterogeneous version at the bottom. So which ones were the sweatpants? Unstructured. Unstructured always fits. Yeah, and I thought about that as athleisure because that's sort of the modern sweatpant, but athleisure is usually sort of tight still. So you got to go like old school, like Kmart sweatpants to get the image that I'm going with here. They're loose, they're forgiving, very breathable. Might need a drawstring even to keep them up, that kind of thing. So this is topolets. Topelets is what it is. For whatever reason, I always put an extra E in there. This one is not available in R, as near as I could tell, as a direct structure, meaning I was too lazy to try to program it in myself. It is an option that is readily available in SAS, in Stata, and in SPSS. So we'll get to see all of those things next time. So big picture, we are making sure that whatever our model for the variance is with respect to time is close enough to what it should be to have faith in the results that follow. We are entertaining the most complex model, unstructured sweatpants, and trying to see if simpler models can do as good a job as that one. Skinny jeans, compound symmetry, tapered jeans, autoregressive, and Topolitz boot cut. Those are my choices so far. So I'll show you an example based on real data starting next time, and we can look at how these things actually translate into a real data set. And the example, by the way, that I'm giving you in this class is not the example that's in the book. So that you will get 2 examples in total if you read chapter 4 and if you watch this lecture and example. All right, I think that's a good place to pause, ask for questions, comments.
I have a quick terminology question with the RGB matrices. So if we're talking in terms of like regular Anova, Manova, we talk about between groups variance or effects as like B within groups, W, total variance, T. Is that analogous to the RVG matrices, or are there any like major differences?
Between groups would not be in here.
Okay,
Because
so that wouldn't be G at all.
Yeah, because these are all residuals after controlling for the fixed effects, and so that would be elsewhere.
Gotcha. Thank you.
So yeah, what I say is total, you might think of as marginal. The key idea is that all of the model parameters are working in one matrix to make the shape, as opposed to multiple matrices that we put back together again to make one shape. The multiple matrices is the G and R family, and then when we put them back together again, it's going to be called V. So lots of letters to go with. All right. Any other questions? All right, then office hours start now. Let me know if you need anything. Have a good afternoon, and I hope to see you Thursday for more about pants. Bye, everybody.